Hello everyone, my name is Mariya Vasileva. I work in the domains of explainability and machine learning, representational learning, and most recently have taken an interest in algorithmic fairness. I'll be talking to you today about the dark side of machine learning algorithms, how and why they leverage dataset bias, and what could be done to pursue algorithmic fairness. With the widespread use of AI systems and applications in our everyday lives, it is important to take fairness issues into consideration while designing and engineering these types of systems. Such systems can be used in many sensitive environments to make important and life-changing decisions. Thus, it is crucial to ensure that the decisions do not reflect discriminatory behavior towards certain groups or populations. We have recently seen work in machine learning, natural language processing, and deep learning that addresses such challenges in different subdomains. With the commercialization of AI systems, researchers are becoming aware of the biases that these applications can contain and have proposed ways to address them. In this talk, we will look into real-world applications of machine learning models which have leveraged bias that can adversely affect downstream applications. We will introduce fairness definitions to combat bias in machine learning systems. Finally, we'll examine different approaches to algorithmic fairness at a high level and discuss future directions that can be taken to mitigate the problem of bias in AI systems. Machine learning and access to big data are revolutionizing the way many industries operate, providing analytics and automation to many aspects of the real-world practical tasks that were previously thought to be necessarily manual. With the pervasiveness of artificial intelligence and machine learning over the past decade and their epidemic spread in a variety of applications, algorithmic fairness has become a prominent open research problem. For instance, machine learning is used in courts to assess the probability that a defendant recommits a crime, in the medical domain to assist with diagnosis or predict predisposition to certain diseases, in social welfare systems for welfare allocation, and in autonomous driving. The decision-making processes in these real-world applications have a direct effect on people's lives and can cause harm to society if the machine learning algorithms deployed are not designed with considerations to fairness. The ability to collect and analyze large datasets for problems in many domains brings forward the danger of implicit data bias, which could be harmful. Data, especially big data, is often heterogeneous, generated by different subgroups with their own characteristics and behaviors. Furthermore, data collection strategies vary vastly across domains, and labeling of examples is performed by human annotators, thus causing the labeling process to amplify inherent biases the annotators might harbor. A model learned on biased data may not only lead to unfair and inaccurate predictions, but also significantly disadvantage certain subgroups and lead to unfairness in downstream learning tasks. There are multiple ways in which discriminatory bias can seep into data. For example, in medical domains, there are many instances in which the data used are skewed towards certain populations, which can have dangerous consequences for their underrepresented communities. Another example are large-scale datasets widely used in machine learning tasks like ImageNet, which suffer from representation bias. Yet another example are the popular face recognition and generation datasets like Celeb-A or Flickr Faces HQ, where the ethnic and racial breakdown of example faces shows significant representation bias. In order to be able to fight discriminatory use of machine learning algorithms that leverage such biases, one needs to first define the notion of algorithmic fairness. Broadly, fairness is the absence of any prejudice or favoritism towards an individual or a group based on their intrinsic or acquired traits in the context of decision-making. Fairness definitions fall under three broad types: individual fairness, whereby similar predictions are given to similar individuals; group fairness, whereby different groups are treated equally; and subgroup fairness, whereby a group fairness constraint is being selected and the task is to determine whether the constraint holds over a large collection of subgroups. In this talk, I will discuss a formal definition of these fairness constraints, examine the ways in which machine learning algorithms can amplify representation bias, and discuss how bias in both the example set and label set of popular datasets has been misused in a discriminatory manner. I will touch upon the issues of ethics and accountability, and present open research directions for tackling algorithmic fairness at the representation level. Let us examine what is wrong with machine learning and more specifically computer vision datasets by beginning with one of the most popular datasets for facial recognition, facial landmark detection, face generation, attribute swapping, and a variety of other applied tasks pertaining to human faces, like Celeb-A. This dataset contains 10,177 distinct human identities, over 200,000 facial images, 5 landmark locations of facial features, and 40 binary attribute annotations per image. There are several different variants of the Celeb A dataset, for instance Celeb A Mask HQ, which is a higher quality, better resolution version of Celeb A with an expanded set of attributes. However, some of the attributes these datasets are labeled with are problematic. For instance, the attractive attribute is also binary as well as chubby and pale skin. It is easy to see why these attributes could be causing problematic and eyebrow-raising results in downstream tasks. If we are to summarize this dataset, take a look at the following generative model published by Sandberg et al., who asked the question, what would those images look like if we, for instance, took all the images of faces labeled positively for the attractive attribute and looked at the centroid of the convex hull of the images by training adversarially on latent space interpolations. The results look roughly as follows, with the so-to-say prototypical attractive image like the one on the top right, and the prototypical big nose image like the one on the bottom right. Clearly, the interpretation of these results is extremely problematic. Yet another dataset recently released was created for the purpose of facial beauty predictions, broken down according to race. The results on the right show what the proposed system in this paper considers most attractive versus least attractive, with the predicted beauty scores shown on top. Clearly, this application raises a lot of questions and borders on the unethical side. Classification tasks like these aside, another bothersome application enabled by a dataset like Celeb A and its derivatives are generative models for human faces. The results here are from the groundbreaking model of Kars et al. Called Progressive Growing of Generative Adversarial Networks, in short GANs, for improved quality, stability, and variation, where the authors introduce a generative model able to synthesize high-quality, high-resolution human faces like the ones shown here, and more samples available on demand on this website. Now, none of these faces are of real people, yet the examples are so realistic that they can be used as a cue for querying facial recognition databases, or training new generative tasks or facial recognition tasks via data augmentation, thus propagating inherent biases present in the original dataset. One such application is the recently published work by Menon et al. Called Pulse, which is a framework for efficient photo upsampling from a blurry, low-resolution image. In the figure on the right, a low-resolution input, such as in the top row, is passed on to the model to produce a higher-resolution image, like the ones in the middle row. And that higher resolution image is further downsampled to produce a result required to be similar to the original obfuscated image. Now, quantitatively and qualitatively, this approach works beautifully and beats baselines on important metrics for evaluation. But upon closer look, we see results like this one. The input image here is clearly of President Obama, which is evident to any human observer, yet based on the representations it has learned from the data it was trained on, the model produces a similar outcome with 4 different initializations, which is essentially an image of a white male. Trying different examples of more individuals who are non-white as input produces similarly concerning results. Another application that has recently gained popularity was created by a startup named Rosebud AI, which synthesizes realistic-looking and diverse fake model images for online retailers or media. The claim appears attractive. Clients no longer need to use real human models or use stock images of models for their purposes, but can distinguish themselves and their brand by showcasing unique individuals. However, imagine what the requirements sheet would look like for an application like this. Would the clients have to specify gender, age, race, and how ethical is the practice of doing that compared to the analogical practice of casting models in the real world? The danger here is increased potential for misuse and discriminatory purposes. For example, requiring only images of models of a certain race or certain age or a certain body type. Moreover, gender and age prediction is not a trivial problem and hides a lot of potential for unethical use of these technologies. Furthering the issue of racial bias in datasets, consider for instance this example, where a machine learning model is trained to classify the type of sport an athlete plays based on the image. Across columns, the top row and the bottom row both show images that are considered similar in the sense that they were either close in pixel space or close in terms of standard visual feature representations. Notice that in the first column, for example, the model predicts basketball for the individual on the top and ping pong for the individual on the bottom, even though the two are very similar in image space. Similarly, in the rightmost column, in the top again, the model predicts basketball, while on the bottom it predicts ping pong, despite both images showing soccer players. Further, notice that the model ends up predicting basketball for every image in the top row. but other sports for every image in the bottom row. You may already have noticed that the predominant determiner of the model's predictions about the sport played seems to be race, even though, according to human intuitive notions of similarity, and even low-level metrics as simple as Euclidean distance in image space, every column of images would be considered similar. Bias in data can exist in many shapes and forms, some of which can lead to unfairness in different downstream learning tasks. There are multiple ways that discriminatory bias can seep into data. For example, in medical domains, there are a lot of instances where the data studied is skewed towards certain populations, which can have dangerous consequences. Mariya et al. Show how exclusion of African Americans resulted in their misclassification in clinical studies, so they became advocates for sequencing the genomes of diverse populations in the data to prevent harm to underrepresented populations. Shaw and Karpas studied the 23andMe genotype dataset and found that out of over 2,000 individuals who have openly shared their genotypes in public repositories, 87% are European, while only 2% are Asian and 2% African. Other such studies were conducted in Fry et al., which states that UK Biobank, a large and widely used genetic dataset, may not represent the sampling population. Researchers found evidence of a healthy volunteer selection bias there. In this slide are shown several different categories of bias. The most important one for this talk is representation bias. Different types of bias occurred at different stages. For example, during the data curation stage, one is likely to run into historical bias, aggregation bias, temporal bias, or social bias. During the algorithm design and training stage, things like popularity bias, ranking evaluation bias, and emergent bias start to creep up. And when the user interacts with the trained model, we have behavioral bias, presentation bias, linking, and content production bias taking place. This issue not only exists in medical fields, but popular machine learning datasets that serve as a base for most of the developed algorithms and tools can also be biased, which can be harmful to the downstream applications that are based on these datasets. For instance, ImageNet and OpenImages are two widely used datasets in machine learning. Shankar et al. Studied and showed that these datasets suffer from representation bias and advocate for the need to incorporate geodiversity and inclusion while creating such datasets. For example, the figure on the left is showing the fraction of each country represented by their two-letter ISO codes in the OpenImages and ImageNet datasets respectively. In both datasets, the United States and Great Britain represent the top locations. In the figure on the right, we are seeing the geographical distribution representation for countries in the OpenImages dataset. In their sample, almost 1/3 of the data was US-based, and 60% of the data was from the 6 most represented countries across North America and Europe. Now, in order to combat the problem of dataset bias, we need to put some formal definition down of fairness. Broadly, fairness is the absence of any prejudice or favoritism towards an individual or group based on their intrinsic or acquired traits in the context of decision-making. Fairness definitions fall under different types as follows. Individual fairness gives similar predictions to similar individuals. Group fairness is concerned with treating different groups equally. And finally, subgroup fairness is a combination notion. It intends to obtain the best properties of the group and individual notions of fairness. It is different than these notions, but uses them in order to obtain better outcomes. It picks a group fairness constraint, like equalizing false positives, for example, and asks whether this constraint holds over a larger collection of subgroups. Fairness methods are not just limited to general machine learning techniques, but because of AI's popularity, they have expanded to different domains in natural language processing and deep learning. From learning fair representations to learning fair word embeddings, debiasing methods have been proposed in different AI applications and domains. Most of these methods try to avoid unethical interference of sensitive or protected attributes into the decision-making process, like the ones shown here, while other methods target exclusion bias by trying to include users from sensitive groups. In addition, some works try to satisfy one or more of the fairness notions in their methods, such as disparate learning processes, which try to satisfy notions of treatment disparity and impact disparity by allowing the protected attributes during the training phase, but avoiding them during the prediction time. Thus, they point out what attributes should not affect the outcome of the decision, for example, in housing loan or credit card decision-making, according to the law. Now let us transition into discussing how we can impose fairness in training machine learning algorithms. One recent groundbreaking idea is to break up this process into three distinct phases. One is a data regulator that has to be concerned with defining the notion of fairness appropriate for the problem and requiring that those constraints are met. The second entity is a data producer that will produce the fair representation based off of those constraints. And the final stage is a data user that does not have to concern themselves with the notion of fairness and simply implements a machine learning task as standard. Now, take a look at the data regulator. Specifically, what the data regulator is going to do is determine some function, and we can go into a little bit of detail later, that includes some notion of what group fairness might mean or some metric of what individual fairness might mean, takes in notions of the sensitive attributes, and also takes in the data that the machine learning model is being trained on. This information is then sent over to the data producer, whose job is to create a representation from this input data that satisfies the fairness constraints required. The estimated representation is then sent together with the labels to the data user, and its job is to train the machine learning model using this representation. The core idea here is that it separates thinking about fairness problems into highly complex sort of conceptual problem of selecting what to measure, how to construct the models for the regulator, and how to learn the representations for the data producer, and then a standard machine learning task at the end for the data user. All these three can be completely separate entities. Zooming in a little bit into the data regulator, its input is the training data, an example set X and a label set Y, a set of sensitive attributes S that may or may not be protected during training, some kind of distance metric or other parity metric rho, and the job of the data regulator is to decide on a fairness criterion nu that's going to take in the machine learning model being trained, F, and the label set for this dataset conditioned on the sensitive attributes that need to be protected. The output of the data regulator is the fairness criteria to be satisfied for the problem at hand. Now, we're going to look at separately at individual fairness and group fairness setting for the data regulator's job. This is the idea behind individual fairness. The goal of individual fairness, broadly speaking, is to ensure that models we train treat similar individuals similarly. Let us concretize the notion of individual fairness by focusing on the mathematical aspects of this framework and answer some important questions about the definition of similarity and the definition of individual quantitatively. The job of the data regulator under this framework of individual fairness is to decide which individuals are similar or should be treated in a similar manner. One approach that could help here is to partition the space in some way in disjoint cells, and those could be as fine or as coarse as we like, such that similar individuals are in the same local region. What the data regulator then has to do is ensure that individuals in the same cell are treated similarly, even if they differ by, say, one feature. We can then say an algorithm is fair if we can partition the space in disjoint sets, and the predictions for similar individuals are similar, or equivalently, the loss for close-by individuals is similar. One big advantage of individual fairness is that it is intuitive, it is fairly easy to explain on a high level, and constraints for individual fairness imply generalization and statistical parity. For more details, one could consult the papers of Xu and Manner and Dwork et al. Among the disadvantages of individual fairness as a criterion are the fact that the quality of results vastly depends on the choice of appropriate metric, which can be a difficult problem, and constructing such a metric often requires a significant domain expertise and human insight, depending on the subdomain of application. Another disadvantage is that optimizing and measuring individual fairness is a lot more computationally expensive than other metrics. In the generic construction, it grows roughly quadratically with the size of the dataset. Switching gears to group fairness, the classifier here should be constructed such that some statistic across the two different groups is similar. Suppose we denote the statistic as nu, what it takes is the prediction model F, the labels Y, and what the group fairness metric is asking is that this statistic for different groups is equal. There are many common measures for group fairness used in practice. One of them is statistical parity, which can be written out as the probability that the classifier predicts one is similar for different groups. Many of the other metrics can be constructed using a confusion matrix, for example. Suppose we have the setup, as in this figure on the right, where elements inside the big circle are from one class and elements outside of the circle, the shaded ones, are of a different class. Suppose the classifier is determined by some linear separator between the two. All of the green points inside of the circle are true positives, and all of the ones falling in the red region are false positives, meaning they were predicted positive by the classifier, but were actually negative. From these measures, we can construct most measures for group fairness like so. For example, For equal opportunity to be satisfied, we can ask that the true positive rates are similar across two groups. For equalized odds to be satisfied, we can ask that both the true positives and the false positives are similar across different groups. It is a challenging problem to pick the appropriate constraint, and different metrics can give us different properties. So it depends on what notion of fairness do we intend for a classifier to capture after we've trained the model. One advantage of group fairness is that it is efficient to compute. It is much easier to measure and enforce, especially with regards to policymaking, as it investigates what happens to an entire group of individuals on average. And there is much more existing work on group fairness than individual fairness in the literature. Some of the challenges of group fairness is again to decide what to measure and equalize between different groups, and the quality of the metric chosen for the particular problem. One issue found in recent work is that, as is the case in real life, group fairness constraints are in danger of violating individual fairness constraints in certain cases. For example, in the context of intersectionality. We can construct models sometimes whereby individuals that are members of several groups simultaneously, which all of us are, we can construct procedures that seem fair on a group level, but lead to adversarial outcomes for sensitive individuals in those intersectional groups. Now, moving on to the role of the data producer, its task is to take in the fairness criteria produced by the data regulator and the input data, and it spits out a fair representation. There are quite a few methods for constructing representations with a particular notion of fairness built in. First, let us talk about the job of the data producer in the individual fairness setting, which is an area of open research. One way to think about constructing this representation is to satisfy the following metric learning problem. Suppose the regulator provides a set of examples which should be treated similarly. The yellow circles in the figure on the right. The producer now tries to learn a distance metric such that similar individuals are treated similarly, which in the metric learning context means that their representations are being pushed closer to each other in their respective embedding space. There are many ways to construct distance metrics for such problems that have been extensively explored in the metric learning literature. But one way, for example, is via triplet losses, encouraging similar examples to be close by in some embedding space, and dissimilar examples to be far apart. So the task of the producer now is to find a metric such that if 2 points are supposed to be in the same set, they end up close together, and if not, they are pushed far apart. The representation learning version of this problem is to find a data transformation, denoted by L on this slide, such that the transformed representations satisfy those distance constraints. For simplicity, the problem here is illustrated with a linear transformation. In practice, we can construct nonlinear transformations such as autoencoders or other neural network mappings. Now, from a group fairness perspective, there are 3 notions the data producer is concerned with. 1. Representation, that is, mapping from the data to the fair representation space. The second one is prediction of a class label, and finally, the fairness metric to be satisfied. The final entity in our pipeline is the data user, which actually takes the fair representation and the labels and simply trains on a standard machine learning task. Now, the data user, the good part about that is that they don't have to be concerned about the fairness criteria to be satisfied and can simply implement off-the-shelf machine learning models without being concerned about satisfying those constraints. So then we can proceed with standard pipelines, off-the-shelf network architectures trained for standard classification regression tasks. Alternatively to the representation learning scenario, there are several different techniques to approach algorithmic fairness, which shall not go into detail with, but we'll just mention briefly here. Generally, methods that target biases in algorithms fall under these 3 categories. Pre-processing techniques try to transform the data so that the underlying discrimination is removed. If the algorithm is allowed to modify the training data, then pre-processing can be used. In processing, techniques try to modify and change state-of-the-art learning algorithms in order to remove discrimination during the model training process. If it is allowed to change the learning procedure for a machine learning model, then in-processing can be used during the training of a model. In post-processing, it is performed after training by accessing a holdout set which was not involved during the training of the model. If the algorithm can only treat the learned model as a black box without any ability to modify the training data or learning algorithm, then only post-processing can be used, in which the labels assigned by the black box model initially get reassigned based on a function during the post-processing phase. And finally, I wanted to show some advantages and disadvantages of alternative representations in terms of ease of implementation, scalability, ease of auditing by the data regulator, and fairness, performance, and generalization ability. Thank you very much.